So in today's lesson, we are going to talk about image processing and analysis with a vision system. And this is chapter 11 from the textbook. I think chapter 12 is fuzzy logic. So what this topic, if you think about it, is pretty boring. It actually talks about the different vision techniques, little bit of algorithms, little bit of mathematics, but unless you use it, you will not understand the true power of these algorithms. So in today's class, what I will do is I will try to kind of go through this theory discussion, and then finally add a demo. And I would encourage you to do this demo with me. So let's go to the basic concept. In this chapter, we are going to talk about what do we mean by image processing and what do we mean by image analysis. Image processing is basically acquisition of data. Image is finally, at the end of the day, it's a matrix. If you have a grayscale image, it's just a one-dimensional matrix. If it's a color image, so you have R, G, and B. So think about it like you have three matrices which are stacked on top of each other. So there is a lot of image data. You can have a two-dimensional image, which is like a 2D, and sometimes you can get the depth information. Sometimes you have to integrate LiDAR or rangefinder or some other means to add additional information to the image. Now, what do we mean by image acquisition? So image acquisition means actually getting the pixelated data from the image. So depending upon number of bits that you have. So in this particular example, think about it is just a grayscale image. And this grayscale image is a 4-bit image. What do I mean by 4-bit image? Which means there are about, if you go from here, 2 to the power 4 gradation of the shades that are describing that image. And that information is kind of encoded in these zeros and ones. So what I want you to think about is, if you look at this image, even though it's not clear, each pixel indicates a color code that indicates the shade of what shade it is, whether it's full white, full dark, or whether somewhere in between. And depending upon what shade it is, what you do is you basically, each pixel has a shade gradation, which is from 0 to 15, because it's a 4-bit image, 2 to the power 4, which is like you have 16 distinct bins that color can be separated into. So each number, 7 in binary is 0, 1, 1, 1, 3 in binary is 0, 0, 1, 1, and so on and so forth. So all this information corresponding to the 10th row is encoded into the series of zeros and ones. At the end of the day, that's what images are. They are series of zeros and ones. And basically, if you have a color image, just like this, you are going to have a R mask, G mask, and B mask. So basically, you have three matrices. When you combine them together, you get the complete color image. Now, image processing can be done in the spatial domain, which is the X and Y or the pixels, or it can be done in the frequency domain, filtering, whether you want to sharpen the image, whether you want to blur the image. At the end of the day, it's like fuzzing or increasing the values, numerical values that each pixel represents. So one important thing that we think about when we analyze an image is we can analyze those in terms of spatial coordinates, pixelations, or we can talk about as the frequency. And if you have a signal that is periodic, what you can do is you can decompose that periodic signal into series of sines and cosines. And Fourier transform is an important mathematical technique to decompose a signal into its constituent parts like sines and cosines. So one thing I want to tell you that even though it says Fourier transform here, what is shown over here is a Fourier series. And I want you to be absolutely clear about what do we mean by Fourier series and what do we mean by Fourier transform. Does anyone know the difference between Fourier series and Fourier transform? Yes.
Fourier transform is an operation you can do going from like time to frequency space, but Fourier series is how you can express like a wave in terms of its component frequencies and amplitudes.
Okay, well, that in terms of the operation, but what this is mathematically. Please understand, when you are looking at a Fourier series, the basic premise is you have a periodic signal, and that periodic signal could be a triangular signal. That periodic signal could be maybe a combinations of sines and cosines, something like that. So you can have a signal that is periodic. But please understand, to apply Fourier series, this signal needs to be continuous. It should go from minus infinity to plus infinity. So that periodic signal should be repeating. It should be periodic and it should be repeating. Only then you can find out the Fourier series. Remember this. Fourier series means that you have a periodic signal that spans entire time axis. So it's periodic. Now, what it means is if I have a signal which is something like this, I cannot apply Fourier series to this because this signal is not repeating. But if you perform the Fourier analysis on this non-repeating signal, that is Fourier transform. So Fourier transforms are used when the signal is non-repeating, and Fourier series is used when the signals are repeating. At the end of the day, what happens is Fourier transform is like when you look at, if once you stretch the time interval from minus infinity to plus infinity, that takes the form of a Fourier transform. Now, here is something very interesting. Laplace transform is a variation of Fourier transform. And if you take my linear algebra class next semester, I will show you, write that derivation for you. Basically, the Laplace transform is nothing but once you apply the Fourier transform has a real part and an imaginary part. When you combine those together and call that an S, like A plus IB as an S function, then the Fourier transform actually becomes Laplace transform. One-sided Fourier transform is nothing but a Laplace transform. Remember this. That will impress the interviewers. One-sided Fourier transform is a Laplace transform. Anyway, that being said, so something I just want to talk about. If you have a signal that is periodic, if you take Fourier transform, what you can do is you can find out the amplitude of the signal and the frequency of the signal. So the idea here is encoding the information. So what do I mean by encoding the information? Imagine if I want to send the data over a transmission line. If I have a repeating signal, then I need to send a lot more data compared to if I just send amplitude, if I just send frequency, and at the receiver end, I reconstruct the signal. Now, basically, to find out amplitude versus frequency representation of a repeating signal, what we do is we use something called as fast Fourier Transform or FFT. FFT is a mathematical algorithm to find out frequency versus amplitude. FFT is the workhorse of the digital signal processing techniques. As a matter of fact, image processing techniques that are used for vision systems, signal transmission, and even the radar and LiDAR and other devices where we are capturing data. Now imagine a case wherein you have a sinusoidal signal which is superimposed by one other sinusoidal. So when you take the FFT, you are going to get two amplitudes and you are going to get two distinct frequencies. If you have more and more frequencies, as you can see, once you take the FFT or once you represent that in the Fourier transform, you are going to get amplitude, frequency, amplitude, frequency, amplitude, frequency, all the content of this signal. But please understand, you can see as the signal has sharp transitions, you will see some oscillations, and that is indicative of the Gibbs phenomenon or oscillations when there are sudden changes. Now, why do we need to perform this frequency analysis? Because please try to understand, every signal has a, basically when you decompose the signal, it's very easy to manipulate the signal. I give you a very simple example. Imagine if a signal has very high noise. Noise is usually a high frequency signal. So if you were to pass that contaminated signal through a low pass filter, then that high frequency noise will get filtered and only the clean signal would come out. If you now imagine a case wherein what you want to do is you are interested in analyzing the noise. So what you do is you basically design a filter, which is the high pass filter, which will take that signal and noise, block the signal and pass the noise out. That is exactly the noise cancelling headphones work. So basically there's a microphone. That microphone is capturing the surrounding noise. That noise gets fed into a high pass filter. So basically now you have the measure of the surrounding noise. That noise signal is inverted and then added to the headphone music, so that sort of the contamination cancels the whole thing. So you get a clean signal. That is how a noise cancelling system would work. And again, if you think about the image, if you want to sharpen the image, if you want to blur the image, if you want to see maybe some of the features of the image, Fourier transform, essentially, if you think about the image is actually a two-dimensional time series. And if you perform, so Fourier transform that we talked about can be performed on one-dimensional time series, time and data, or it can be performed on 2D data, wherein you have the data around X, you have the data around Y. So image, typically we perform two-dimensional Fourier analysis and get the spectral content of it. And then again, you can capture the Fourier modes and you can retain the principal components. And depending upon the principal components, basically you can shrink the image, or basically if you want to sharpen the image, you run that through some type of a masking function, which is again a filtering function, and so on and so forth. Now, if you think about it, I want you to just think about the frequency content of an image, and you have this image. At the end of the day, what is an image? Image is a matrix. So basically you have a two-dimensional data and each pixel has some type of color intensity. If it's a grayscale image, then there will be the gradations of black and white. If it's just black and white image, each data here could be either 0 or it could be 1. It could be white or it could be black. So now imagine what you want to do is you have an image, something like this, you zoom in and you see the blob and you want to somehow analyze this blob. So I want to find out whether that 9 comma h, whether it's a noise or whether it's part of the signal. So what I do is I look at the pattern and I see that at 9h, all of a sudden there is some variation in the pixelation. The intensity suddenly changes. So that could be an indication of noise. However, if I go forward, if I go to 9K, 9L, 9M, I see the uniform intensity. That is an indication that it could be a line. So I want you to understand at the end of the day, image processing is you are dealing with the matrices. That these matrices have data. And at the end, what you do is you perform large numerical computations on these data sets. And finally, that data gets represented in the modified image. Now, there is a concept which is called as the resolution and quantization. So resolution, probably you know that if you have 480 by 320, 240 by 160, 120 by 180, 60 by 40, depending upon the resolution that you want, the image can become blur or image can become sharpened. Quantization means how many gradations you have available to represent particular pixel. If the quantization, which is 2 to the power 4, which means you have 0 to 15, 16 grades of shade. If 2 is just 2 to the 2, which means if you have it's 4, then only you have 4 shades that you can represent. So as you can see, more the resolution, more the quantization, better image that you get, which means you can represent a teeny tiny change very nicely with a higher quantization, and basically you can capture the entire image with a higher resolution by increasing the resolution. So some of the important questions here that we talk about is data points, how many pixels, and how much information is available. And again, so this talks about the quantization. So for an example, if it is just 2 gray levels, then as you can see, that image is not that great. If there are 4 gray levels, then you can see slight variations. You can add 8 gray levels, you can add 256 gray levels. So there are 256 shades of gray that is representing this picture. Now,
that means it's 256 bits.
So yeah, it's 256. So 256 gray levels is 2 to the power 8. So it's 8-bit. So the first one is 1 bit, 2 to the power 1. Second is 2 to the power 2. Third is 2 to the power 3. And then you have 2 to the power 8 is 256. So think about it like you have a palette and you have 256 shades available. So you can actually represent that picture much better. Now, there is an important theorem which is called sampling theorem. And I want to talk about this. What is sampling theorem? So imagine if you have a signal. If this signal is varying something like this, okay, this is a continuous signal. What I'm going to do is I'm going to take the snapshots of this signal. So if I take a snapshot here, 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 and basically plot that data, then I have some crude representation of this periodic signal. It's not accurate, but at least I have the data on the highs and lows and the transition points. So I have the data on lows, highs, and transition points. If I want more accurate representation, I need to increase the sampling frequency. I need to sample more often. So there is something called as Nyquist theorem. That theorem states that if you want to capture the signal, you should be sampling at twice the frequency of the maximum frequency in the signal. What that means? Please understand, if this signal is running at 1 hertz, it's repeating 1 times a second, to capture the high and low, you need to sample the signal at 2 hertz, which means you will be able to capture highs and lows and zero crossing. So Nyquist theorem states that the sampling frequency must be minimum 2 times the frequency of the signal. That's why the example that I gave in the last class, the human speech can have frequencies from 20 hertz to 20,000 hertz. That why the CDs, they are recording the sound at 44 kilohertz, so that it's capturing all the frequency content in the human speech. So one thing I want to tell you is there's an interesting concept that is happening in the field of sampling. So which is, I will talk about it in just a minute, but please try to understand, you have a sinusoidal signal. If you take the snapshots, then what you do is you can plot that snapshot data, and then you would be able to reconstruct the signal. But the problem here is, if you don't take snapshots properly, if your snapshots don't follow the sampling theorem or the Nyquist theorem, then it may be possible that the signal that you will reconstruct may not look like the original signal. Once again, let me repeat. So here I'm sampling here, 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 here. Now imagine, instead of that, I just sample here, I sample here, I sample here, and I sample here, and I reconstruct. Then what I'm gonna get is I'm gonna get just a horizontal line, which means my captured signal does not look anything like the actual signal, because I'm not sampling at the right frequency. So this is called as aliasing. And I have to be super duper careful about this. You will hear this word aliasing, aliasing, aliasing all the time. What does that mean? Aliasing means you have an original signal, did some sampling, you did some sampling, and then reconstructed a signal, but that reconstructed signal is different from the original signal that you sampled, and that in general is called as aliasing. So please understand, aliasing means that you have this signal, but you sample it and then use the sampled signal and you plot it, and you realize that the sampled signal does not look like the original signal, and that is the effect of aliasing. So the idea here is, you can look at the sampling, you can look at the signal frequency, and your sampling should be at least more than twice the original signal. Everyone understood this? Any questions here? Yeah.
So why can't we just capture the signal?
What?
Why can't we just capture the whole signal?
Yeah, you can capture the whole signal, but the problem to capture the whole signal is you have this analog signal that is continuous, but your device is digital, which means you cannot capture that entire signal unless you have a very high resolution, high-end electronics. So what you want to do is, finally, the computers are digital, so you have to sample. You can't capture the whole signal, but you can increase the sampling frequency. But if you increase the sampling frequency, that increases your storage requirements, that increases your power requirement, And that again, if you, for an example, if you have a signal at gigahertz, clearly you need some type of a sampling that is twice gigahertz the sampling frequency. So that equipment cost also increases. So everyone is clear, and I need to write this down because I'm going to violate that principle in just a second. So this is the Nyquist theorem. Nyquist or sampling theorem. Remember this all the time. Sampling. Basically, what that means is sampling frequency, F sampling, is greater than F, so 2 times F signal. Example, if you have F signal, is running at 1 hertz, 1 cycle per second, or then your sampling, F sampling, should be minimum 2 hertz. Everyone understood this? Everyone clear about this? This is not true. This is something that people thought for last 100 years. Now there is this new field which is called as compressed sensing. And this is very intimately related to the linear algebra. So I will teach this in my linear algebra course. So what is this idea? Let me show you what is happening here. Imagine that you have a signal, and when I'm following Nyquist criteria, what that means is something like I'm sampling here, I'm sampling here, I'm sampling here. So I take this point, I take this point, I take this point, I take this point, and I move on. Okay. So the basic assumption here is that this time period between each sample, T sample, is constant. Are you with me on this? So basically, Nyquist sampling theorem, based on the assumption, and nobody violated this for about 100 years. The idea was that when I'm going to sample, I'm going to have this fixed time period wherein I'm going to take the snapshot and then use this to reconstruct. About 20 years ago, Terry Tao and other researchers from UCLA, Terry Tao is a professor in UCLA, they said, what if I do something like this? Imagine that I have this signal, something like this. I have this signal, and instead of sampling it at a constant interval, instead of sampling this at a constant interval, I would change that interval randomly. Which means what I would do is, I would do the random sampling. So what that means is my time samples are not going to be spaced at uniform time interval, but this time interval will be randomly varied. What that means is there is a high likelihood, because of the random sampling, I could capture the slowly moving component of the signal, and I can capture the fast moving component of the signal. That is the fundamental principle of compressed sensing. What does compressed sensing mean? Compressed sensing means that you can violate the Nyquist criteria if you randomize your time samples and capture the signal. So you may capture this part, you may capture this part, you may capture this part, you may capture this part. As long as your sampling is random and you do that enough times, you'd be able to capture all the trends in the signal that would allow you to reconstruct. What that means? is you can reconstruct with a very small number of samples. Believe it or not, it works. I didn't believe it, but I ran my simulation myself, uh, and it actually works. It's beautiful. I give you another example. MRI images. I don't know if you have seen MRI and CT scan images. About 15-20 years ago, when they used to do MRI and CT scan, you won't be able to see those images clearly immediately on the screen. They will say the images will be ready after 30 minutes, 40 minutes, 50 minutes, because those MRI or CT scan images, there is tremendous amount of data coming in. So to capture all that tremendous amount of data, you need a very powerful hardware, you need a lot of storage, and afterwards you need to process all that information. But nowadays, if you do MRIs or CT scan, you see everything immediately. Why? Because they are doing this compressed sensing. So basically the whole signal is captured by the principles of randomization. And there are some conditions that need to be satisfied so that compressed sensing actually works. Okay, there was a question here. What was the question?
I got the answers. This is only for periodic signal. Periodic signal cannot be used, but for compressed sensing cannot be used in aperiodic signal.
So basically, you can do compressed sensing for aperiodic signals as well.
But then how can we find trend, because there is no periodicity?
Yeah, but so I'm not an expert in compressed sensing, but compressed sensing has been used for periodic signal, aperiodic signals. As a matter of fact, for the images, they do compressed sensing. I'm not an expert in that, but that is an area of active research. And if you want to become an autonomous, if you want to become a perception engineer, if you want to get in the field of vision, computer vision, application, autonomous driving, then compressed sensing is going to be an important field. Because think about it, you have this LiDAR data coming. You need to capture that data and process that data in real time and to somehow understand what's going around the vehicle. You have to make some real-time decisions. If you capture the whole data, if you process the whole data, if by that time that data analysis is done, the vehicle may get into an accident. So if you want to become a perception engineer, if you want to become a computer vision person, compressed sensing is an active area of research. And it's not difficult. And basically it kind of makes sense that if I change this time period randomly, I should be able to capture the most of the components of the signal. Yeah.
Limit for the random, like the time random.
Yeah. So there is tremendous amount of mathematics that goes behind compressed sensing. To be honest with you, I don't understand that because they deal with randomness theory, martingales, and all that type of stuff. But there is huge mathematical machinery that backs compressed sensing. I will talk about it a little bit in my linear algebra course in spring, because I think, and actually this comes from the linear algebra, believe it or not. Finally, you are dealing with the matrices. You can, SVD is not compressed sensing. SVD, PCA is not compressed sensing.
Don't you take the whole array and then make it into a smaller array?
Yeah, basically you find the principal components and all that type of stuff, but that is different than compressed sensing. So compress in SVD, you don't change the sampling size. You basically do the SVD, you find the principal components, you discard everything else, just get the singular value, arrange singular value, and try to reconstruct. SVD can be used for noise reduction, SVD can be used for image compression and all that type of stuff, but compressed sensing is something else. Compressed sensing is more than SVD. Compressed sensing is not compression. So basically data compression is not compressed sensing. Anyway, so again, you can actually, all these functions are available in MATLAB, and I will actually jump onto the MATLAB in just a second. But try to understand what you have is, you have this image, but this image has only gray level intensity between 80 and 150. So this image is not very clear. What I could do is I could spread this. In other words, in MATLAB's word, they can resize it or reshape it and then have this intensity spread from 0 to 255 that makes this picture clearer. So histogram is one technique that can be used to sort of refine the image. Again, what you can do is you can adjust the brightness and contrast. So basically you get the original image, you look at the histogram, pixelated histograms, manipulate the data distribution, and then you can actually brighten the image or make it sharpen or add contrast to it. Thresholding is like coming up to the threshold, and what you can do is you can display the path of the pixel, or you can turn on or off the pixel, or basically you decide an intensity. Below the intensity, you just assign that pixel to 0. So you can change the threshold and basically you can manipulate the image. Then you can do the multimodal thresholds. So you can have the thresholds on different time scales, and that will affect the image. And again, why is this thresholding is needed? The obvious reason for that is if you want to detect objects, if you want to detect shapes, or if you want to detect any other feature, these are the important tools. Now, at this point, what I want to do is I want to show you a small demonstration of how these things work. Because believe me, just discussing all this is not that exciting if I were to show you how this works inside the MATLAB. So what I'm going to do is I am going to set up my MATLAB, and if you have MATLAB, please start it. And then I have this small USB webcam. For my online students, what I want to do is I want to show you this setup. I don't know if you can, let me see. If you can see my setup here. I'm trying to show you on Zoom. Okay. Can you see my setup? I have a small webcam. Actually, and then I have that webcam attached to my computer. And then what I'm going to do is I'm going to go to MATLAB. I'm going to go to MATLAB. Okay. Can everyone see my MATLAB screen? And what I want to do is I have this sort of this graph paper. I'm going to place my vision system on here. And then what I want you to do is I want you to go to MATLAB, go to apps, and then in the apps, there is an image processing app. So image acquisition, click on this. So go to image acquisition, app, and then if you have the drivers, then you should be able to get the data. For some reason, it's not detecting my webcam. So what you can do,
What was the image acquisition to render?
yeah, so if you go down here, image processing and computer vision. So basically capture image acquisition. And then you can actually capture the image. And if you are having the same problem as me, then what you need to do is you need to go to MATLAB add-ons and webcam USB support for webcam drivers. So and if that is the problem, then turn it off and turn it on. So basically go to MATLAB. So go to MATLAB and now go back to apps and then go to the image processing, image acquisition, and now let's hope that it captures. For some reason, it's not capturing. Well, for some reason, my USB webcam is not working. But what I would recommend is try to do the image acquisition from MATLAB. And then what you can do is you have this image region analyzer, you have image segmenter, you have a registration estimator. All these are the algorithms that we talked about. Let me just no idea why this is not working. So I'm going to try one more time. Yeah, so this is the software that you want to download. MATLAB support package for USB webcams, and then you should be able to get the data from the webcam. So for some reason, it's not working right now. So let me just continue the theory part. Yeah. I don't know what happened there. Before coming to the class, I checked it and it was working. So let me see. It's just a matter of driver. So, but please try. And see if it is working with your cases.
Oscar,
Yeah.
what can be a reason that like image acquisition is not being displayed or
Yeah, I don't know if it is because of the Zoom is yeah, he got it working. So I don't know if it is because my Zoom is also on, because what happens is when you have the Zoom, it is actually has access to the GPU. So that may be the reason that my webcam is not working.
If you stop the video on Zoom, you might be able to access the webcam.
Okay, if I stop the video on the Zoom, and then so I don't know, I mean, let me see, let me check real quick. Apps. But just try, I think it should work with your webcam as well. So go to image processing, go to image acquisition. No, it's not. I don't know if it is because of the Zoom. But once you, what you should see is once you got that image acquisition toolbox, then you will see that can actually acquire the data, that can process the data, that can do the thresholding, and it can do a lot of interesting things.
You can use webcam function to see whether it's detecting.
No, it's not detecting, because if it is detecting, you will see in the hardware browser here. So yeah, no. So I don't know if it is why it is not working, but I would encourage you to take a look at it. Okay, so as a matter of fact, even my screen is not being displayed now. Anyway, so the idea is I would encourage you to do this, but since I'm having technological difficulties, what I want to do is I want to show you, or I want to give you the background of the setup. So here is the idea. What you have is you have a robot. Say it's a 2 degree of freedom manipulator. Okay, you have this robot. On top of it, here you have a webcam. And if you, what you want to do is you want to capture the image. So this is the robot. And this is the webcam or camera. Now I want you to understand that this robot is attached at certain location. This is the 0, 0, 0 location for the webcam. How, I mean, so for the robot. And now this webcam is looking at this area that has its own coordinate frame. So what I want to do is, I want to show this in a top view. So I want you to think about it like this. This is the whole board. On this board, what you have is you have the 0th frame of the robot. So your robot is over here. So this robot is over here. And you have this webcam. That webcam is kind of looking at this whole picture. Say, for an example, this is what the webcam is looking at. This is what the webcam is looking at. If you look at the coordinate system of this robot, the coordinate system of this robot maybe this is say X, and say this is Y, and Z is coming out. So you have X, Y, and Z. However, when you look at the webcam 00 is going to be here. So for the webcam, you are going to have this axis and you are going to have this axis. And I want you to think about this setup for a second. The idea is I want to take the picture of this whole setup. I want to take the picture of the whole setup, and I want this robot to go a particular location and maybe grab the object which is over here. So how would this process work? First of all, this webcam is going to start pixelation from here. So webcam doesn't have any relationship to the meters or centimeters or some dimension. This photo or this picture is only pixels. So for an example, if your webcam is 640 by 480, that means it has 640 axes. So there are 640 pixels here. And there are 480 pixels around Y. So what's going to happen is, when you are going to take the photo from the webcam, or you are going to take a picture, this particular object will be at certain pixel location. Now what needs to happen is, this pixel location needs to be converted into the distance measurement. So there will be a scale factor. So you need to know, you need to find out 1 pixel, what is the pixel in the X direction and pixel in the Y direction, what does it correspond to the actual dimension on the world frame. Then next thing what you need to do is, you need to take into account the offset. So let me pose the problem. I have this webcam. This webcam is capturing this image. This is the robot. I place an object. I take an object. I place the object somewhere in this region, and I want this robot to go to this object. I want this robot, the end effector, to go to this object. Now, how would you do this? What are the steps using computer vision? Step 1 is I will take the picture. I will find out the pixel location where this object is located. I will find out the pixel location where this object is located. I will convert that pixel location in terms of X and Y. But please understand, I have this constant offset from the base frame of the robot to the base frame of the picture. So I take care of that offset, and then I find out the distances, the X distance. I'm going to call this X robot, and I'm going to find out Y distance of the robot. And then I would run an inverse kinematics on this XR and YR. So after I do the inverse kinematics on XR and YR, I will find out the joint angles corresponding to the first joint. I will find out the joint angles corresponding to the second joint, and then add that command, give that signal so that the robot can go from this location to this location. And maybe if you have an electromagnet or if you have an end effector, you can grab that object. Everyone understood this? Actually, it's much cooler when I actually show you the demo, but for some reason, I don't know whether it is because of the Zoom or because of the setup, that system is not working. But this is what I would like to do in class, and I'll see what's going on. I promise it worked before I came here. So the idea is you have one servo here, you have other servo here. I take the picture. This picture gives me the image. What I do is clearly I need to use some type of image technique, either the segmentation or thresholding, to find out that this is the object. And once I do, I know that this is the object. If it's a circular object, I can find the centroid of that circular object. And there are MATLAB functions and image processing tools that will find the centroid of a connected body. Then once I find the centroid of that connected body, then what I do is I find out the distance, which is in pixels in terms of the world coordinates. How do I do that? Super simple. I take the image and actually, as you can see, I put a scale. So I know 1 pixel is equal to maybe 2 millimeters in X direction. 1 pixel in Y means 1 millimeter in Y direction. So basically, I do this pixel to 480 by 680 pixel in terms of scaling. So I can actually put a scale here. I can put a scale here, and I know exactly what is the distance of this guy, because robot does not understand pixels. Robot understands distance. Then after everything is done in distance, I find out the distance of this object with respect to the robot's inertial frame. Everyone understood this? And at that point, I solve the inverse kinematics problem, get the joint angles, program those joint angles, and actually get that robot to move. Everyone understood this? It's way cooler when I actually show it to you. Anyway, so the other thing which I want to show you, yeah. So yeah, again now, okay. You are going to take a webcam picture. That webcam picture will be either in YGB. So depending upon RGB, or it could be in a different. So basically, pictures can be represented as combination of red, blue, and green. This is one coordinate system to represent pictures. But there are 3 more coordinate systems like YR, GR, BR, or there are different coordinate systems. Some images are better analyzed in particular coordinate system. So think about like a cylindrical coordinate system or Cartesian coordinate system. So your webcam is going to give you an image. You have to process that image. Basically, what you need to do is you need to get this RGB image, convert that into a black and white image, then do the edge detection, and then you have to use this thresholding and all other algorithms to find out where that image is, and then use that information, find the pixels, convert those to the distances, and then use your inverse kinematics to have the robot go to that direction. And it's very interesting. The other thing which I want to show you is you can do that very easily with an Arduino. So for an example, if you have an Arduino Uno or Arduino Mega, what you can do is you can connect it to the small servo, and you can use the Arduino servo library and then basically program the servo. So let me show you. If you have MATLAB, I would encourage you to quickly look at this Arduino servo library that can, so go to Simulink, and there is this blank model. It's actually super simple. I just want to show this to you. And in Simulink, just go to this Arduino block. Okay. Go to library browser and go to Arduino. And if you go onto this Arduino servo board, let me see. So continuous servo write. What you can do is you can actually go here, map the pin of the Arduino. So for an example, what this means is you can choose the pin number and it gives you the directly servo setting. If you have a continuous servo, then you can run that from -90 to +90. So the servo will run clockwise, counterclockwise, continuously. If you have a discrete servo, then what you can do is, this is servo motor. So, or you can use, there is another one, standard servo write. So basically here, what you can do is you can select the pin number and supply 0 degrees, then that servo will go to the 0 degrees. If you supply 90 degrees, that servo will go to 90 degrees. Supply 180 degrees, that servo will go to 180 degrees. So what that means is if you have a 2 degree of freedom robot arm, you can actually use, if it's a discontinuous servo, then you can use standard servo write, send 90 degrees, send 90 degrees. First servo will get rotated by 90 degrees. Second servo will get rotated by 90 degrees. So you can actually control your robot using MATLAB. So check this out. This is actually very interesting. Okay, with that, I'm going to stop here today. And then I will figure out why, for some reason, my setup didn't work. But if you have any questions, I would be happy to answer.